Welcome to Brain Vision.
In this problem, we're asked to calculate the half-life for 1 gram of samarium-147 isotope that undergoes alpha decay. I wrote out the reaction here. We have samarium-147 that decays into a daughter element of some sort that has atomic mass number 143 and atomic number 60, and the other decay product is the alpha particle. And an alpha particle has an atomic mass unit of 4 and an atomic number of 2, and it is a helium. It's a helium nucleus. So the other information given in this problem is that the activity of the samarium-147 decays at a rate of 120 decays per second. And we're also given that the abundance of samarium is about 15%. So the first step of this problem, we can figure out two of the constants that are needed in order to solve for these half-life, given the relationship that activity is the product of the decay constant lambda times the number of nuclei present, n. Given this relation, we can find out lambda as the proportion of activity to number of nuclei present. But we don't have the number n yet, so we'll need to determine that from the atomic mass of samarium-147. Well, we know that the atomic mass is roughly equal to the atomic mass number of an element. We can use that in to figure out the number of nuclei present, or the number of atoms present of samarium-147 as follows. We can enter in our 15% abundance times the 1 gram that we're asked to solve for. Both were pieces of information given in the problem, and divide this mass of samarium-147 in the numerator, divide that by the atomic mass of samarium-147, which is roughly equal to 147 atomic mass units, and as well as dividing this mass by the grams to atomic mass unit conversion factor of 1.66 times 10 to the negative 24th. Doing that, we find we have that there are 6.15 times 10 to the 20th nuclei present in the sample. So dividing this figure, we can rather do the division. Now that we have a figure for n, we can divide into the activity value we were given of 120 decays per second. Divide that value of r by our 6.15 times 10 to the 20th nuclei. And we get a value of 1.95 times 10 to the negative 19th. And that is the decay rate in, the decay constant in units of reciprocal seconds. Now that we have the decay constant, we can use that to solve for the half-life in seconds of our of samarium-147. We know that because we have the relation of half-life to decay constant of natural log of 2 divided by the half-life in seconds. So we can rearrange our factors in this and divide the numerical approximation of logarithm 2 by our lambda that we solved for in the previous step. Doing this, we find that the half-life in seconds of our sample is 3.55 times 10 to the 18th. Seconds. That is a big number, so it'd probably be a little bit less unwieldy for us to convert it to years. To convert seconds into years, we have to find out how many seconds there are in a year and divide by that number. I do it as follows. There are 365 days in a year, and there are 86,400 seconds in a day. So doing this division, we find that we are left with 1.1 times 10 to the 11th years for the half-life of samarium-147. And that's our answer.
Welcome to Brain Vision.
30.82. Almost all of naturally occurring uranium is uranium-238, and most of the rest of it is 235. And we're imagining that today we have a sample of uranium that's 0.72% uranium-235, and the rest is 238. And so we want to find out what the percentage of that, what percentage of the sample would have been uranium-235 1 billion years ago, and what will it be 100 million years from now? So just to make this sort of easier, let's assume that today, because we're not told what the size of the sample is, and like we could do it just in terms of like percentages and stuff, but since the total amount changes over time, it's a little bit tedious. So let's just say we have a 100-gram sample, and because at the end of each part we're doing a percentage, it sort of doesn't really matter what arbitrary amount we choose. So 0.720 grams of the 235 today. So we have our usual decay equation, n equals n naught e to the negative lambda t. Now, with this case, we know what n is, because that's the value today after a billion years has elapsed. So we just want to solve this for n naught. So we just get e to the positive lambda t. So for the 238, and we can, the number of atoms is proportional to the mass, right? So we can just directly put in our 99.280 grams for 238 and 0.720 grams for the 235, and it'll all work out. So we get 115.94 grams of the 238, and 1.7 or 927, sorry, 927 grams of the 235. And so this works out to be 1.63% uranium-235. So we can see that we had a larger fraction of uranium-235 in the past, which makes sense because we can see from the difference in half-lives here that the half-life is almost 10 times less for uranium-235, so it decays faster. And so more of it has decayed since, a billion years ago. And so the percentage of it in the sample should have been higher back then. And similarly, we should expect that, 100 million years in the future, there's going to be an even lower percentage of the 235 because, again, it's decaying faster. I think that direction is maybe a little bit more obvious. So now we just run this calculation in sort of the usual way. We're looking into the future rather than back at the past. So we'll have 97.752 grams of our uranium-238, and we'll have 0.6525 grams of our uranium-235, and so 100 million years from now, this sample is going to be 0.663% uranium-235 out of the uranium that's present. Obviously, all of the uraniums that have decayed since the sample was a billion years old, and then 100 million years into the future, obviously there's going to be other atoms in there. But out of the uranium in the sample, it's going to go from 1.63% uranium-235 a billion years ago, 0.72% uranium-235 out of the total uranium today, and then 0.663% in 100 million years.
Welcome to Brain Vision.
In this problem, we're asked to determine the radioactivity, R, of a banana that contains 420 milligrams of potassium. In potassium, it's potassium 40 that is the radioactive constituent, the radioactive isotope. And if you look up in Appendix B, the percent abundance of potassium 40 is 0.0117%. The half-life of potassium 40 is 1.248 times 10 to the ninth years. So in order to find the radioactivity of the banana, we will need to first find the decay constant given this half-life. We will also need to find the number of nuclei of potassium 40 isotope that's present in 420 milligrams. So in order to find the decay constant, we have a formula here that in which the natural log of 2 is in the numerator and the half-life in terms of seconds is in the denominator. We're given a half-life in years, so we'll have to convert it before doing the division. And the conversion goes as follows. We have the actual half-life in years. We multiply it by the number of days in a year and multiply that by the number of seconds in a day. Doing that, we get a result for our decay constant of 1.79 times 10 to the negative 17th reciprocal seconds. Next, we need to find the number of nuclei in our 400 milligram sample of potassium with the abundance of potassium 40 isotope. Remember that we were given a percentage of 0.0117. So in order to have a fraction of that, we move the decimal point over to the left 2 decimal places. We multiply that by the amount of total potassium we have in our sample, which is 420 milligrams. This numerator is the amount of potassium 40 in milligrams. The denominator, we can approximate the atomic mass of potassium 40 using the atomic mass units, and the atomic mass number of potassium 40 is 40. This is an approximate. However, for this purpose of significant figures, it will do for us fine. And of course, we need our conversion factor going from atomic mass units to milligrams. That way, we're left with a unitless count of the number of nuclei. Plugging in these numbers, we find that there is 7.40 times 10 to the 17th nuclei. And finally, using the decay constant and the number of nuclei, we can compute the radioactivity of our sample. That is simply the product of the two. And from above, we have 1.79 times 10 to the negative 17th reciprocal seconds for our decay constant. And we have 7.40 times 10 to the 17th nuclei. Conveniently for us, the the powers of these exactly cancel, and if we multiply 1.79 times 7.40, we are left with 13.2 decays per second. And that's our answer.
Welcome to Brain Vision.
30.84. So we have the decay of neon 23 into sodium 23, and it undergoes a beta decay. And so we want to find the maximum kinetic energy that the electron can have, as well as its minimum energy, and then say what the energy of the neutrino is in either case. And we're to ignore the recoil of the daughter nucleus. So now the total kinetic energy of the electron and the neutrino is going to be the Q value of the reaction. And so we should focus on getting this, and then sort of the max and min, etc. of these is going to be sort of obvious. So then the Q value is going to be C squared times the mass of the neon, which is given in the text of the problem, minus the mass of the sodium, also given in the text of the problem. And so then this is 4.6 mega electron volts. And by using the atomic masses, this accounts for, the emitted electron, our sort of usual way of doing things. So does it ask for? Yeah, it asks for the maximum first. So the maximum kinetic energy the electron can have is just the entire energy, and then the neutrino gets none. And then similarly, the minimum the electron can have is 0 when the neutrino gets all of the kinetic energy.
Welcome to Brain Vision.
In this problem, we're asked to show that in alpha decay processes, the kinetic energy of the daughter nucleus that's created in the alpha decay has a kinetic energy equal to the fraction of 1 over the sum of 1 plus 1/4 the atomic number of the daughter nucleus. That entire fraction times the total kinetic energy. So in order to prove this, I need to define the symbols we're going to use. As I just mentioned above, A sub D is the atomic mass number of the daughter nucleus. We'll call M sub D the atomic mass of the daughter nucleus in our derivation. Vector V sub D, we're going to call the velocity of the daughter nucleus. And similarly, for the alpha particle, we have M sub alpha, which is the atomic mass of the alpha particle. And we have vector v sub alpha for the velocity of the alpha particle. The critical properties we will utilize in order to prove this is first the conservation of momentum. That is the sum of all of the players in this reaction, each of their momenta, when you sum together each of their momenta, it equals 0. And that should be a 0 vector to be precise. Using this conservation property and noting that the velocities are in opposite direction, we can express this conservation of momentum as follows. md times scalar velocity, which is speed, of the daughter nucleus is equal to m sub alpha of the speed of the alpha particle. The second property we will utilize is conservation of energy here. And since there's no mention of potential energy in this equation, all of its that we're considering is kinetic, energy is conserved as follows. The total energy of the decay process is equal to the kinetic energy of the daughter particle plus the kinetic energy of, and that's the daughter nucleus rather, the plus the kinetic energy of the alpha particle. Each of these can be expressed in their usual form. 1/2 times, for the alpha particle, the kinetic energy is 1/2 times the mass of the alpha particle times its velocity squared. Similarly, for the kinetic energy for the daughter nucleus, it's 1/2 times its mass times its velocity squared. And using these two above, starting with the conservation of momentum, we can express the magnitude of the velocity of the daughter nucleus as a fraction of the velocity, the magnitude of the velocity of the alpha particle, which is m sub alpha over m sub daughter times the velocity of the alpha particle. So with this, we can plug in our equivalent for v sub d into our kinetic energy for the daughter nucleus. I did that here. We can rearrange the factors such that we see that this kinetic energy of the daughter nucleus can be expressed as a fraction of the kinetic energy of the alpha particle. You see the 1/2 alpha particle here that I pulled out of the squared term, and the velocity of the alpha particle squared. So because we now have a kinetic energy of the daughter nucleus expressed in terms of the kinetic energy of the alpha particle, we can insert that, one of the two, into our energy conservation. And I've decided that rather that we can do the reverse and express the kinetic energy of the alpha particle in terms of the kinetic energy of the daughter nucleus and insert this relation into the conservation of energy relationship above, this guy here. And that way, doing this, we can get rid of this kinetic energy of the alpha particle in our final relation and only consider kinetic energy total and kinetic energy of the daughter. So let's do that here. The kinetic energy of the daughter, just as before, and plus the fraction of the kinetic energy of the daughter that we're substituting in for the kinetic energy of the alpha particle, the sum of these two equal the kinetic energy total. We can factor out the kinetic energy of the daughter and express the kinetic energy as so. And then we can divide both sides by this coefficient, 1 plus the fraction mass of the daughter divided by the mass of the alpha particle. And finally, we can realize that the atomic mass of the daughter particle is almost can be well approximated by the atomic number of the daughter nucleus. And same goes for the atomic mass of the alpha particle. It can be well approximated by its atomic mass number, which is equal to 4. Plug in each of these into our fractional term there, and we get the answer of kinetic energy of the daughter is equal to 1 plus 1/4 the atomic number of the daughter nucleus. This whole fractional quantity times the kinetic energy total is what we're asked to show. We have that here. Let's box it. For part B, we are asked what percent of energy is carried off by the alpha particle in a specific radon 226 isotope alpha decay reaction. And we have this nice expression that we just derived. If we assign, since we're working in percentages, the kinetic energy total of 100, then we can insert the relevant numerical values into our expression for a kinetic energy of the daughter, specifically the atomic mass number of radon, the atomic mass number of our alpha particle, which is 4, and which we already determined in the above relation, and our kinetic energy of the entire reaction that we're assigning a value of 100 for convenience. If we plug in these values, we find that we are left with a value of 1.77% for the amount of kinetic energy carried off by the daughter. Well, we're asked for the amount carried off by the alpha particle. And since energy is conserved, the kinetic energy of the alpha particle must be the kinetic energy of the total reaction, which we've given a value of 100, minus the kinetic energy of the daughter, which we just determined as 1.77. Doing that subtraction, we're left with 98.2. And since I used a value of 100, we can give that a percentage. And that is our answer.
Welcome to Brain Vision.
30.86. So the decay series can be sort of grouped into 4 families that depend on the mass numbers in the series, where they'll all have the form of 4n, 4n plus 1, 4n plus 2, or 4n plus 3, for n being some integer. And first of all, this is, this covers every integer of this form. These are sort of the integers modulo 4. So every integer is either divisible by 4 or has a remainder of 1, 2, or 3 when divided by 4. So it can be written, any integer can be written one of these 4 ways. And now we've sort of justified that this works. Just in terms of you can actually write every integer this way. Now the reason why we've picked 4 is because the alpha particles have a mass number of 4, and alpha emission is the only way for the mass number to change. And so given that this is the only way for the mass number to change, it's sort of easy to see that the mass number always has to change by 4, and that means that the new number you end up with is going to be in the same family. So if we have 4n minus 4, then this is 4 times n minus 1 is just 4 times some new n. And similarly for 4n plus I, where I is 0, 1, 2, or 3, minus 4 is going to be 4 n minus 1 plus I is going to be 4n prime plus I. So you can't get out of which family you're in as you go down the decay series.
Welcome to Brain Vision.
Hey everybody, so we want to know if the aluminum absorbs a neutron, what does it become? Does it decay to beta plus or beta negative, or what will the product of nucleus be? So we have 27 aluminum and 13 here down here. And let me write that a little nicer. Okay, and so we have a neutron absorption. So that means we have 1 neutron here, 0 here. And so actually let me write this a little nicer here. So there we go. Okay, so what happens with this? This is 0, not B. We want to know what the reaction would be. So this is going to be basic chemistry. And we know since this is 0 right here, it's still going to be 13 down here, okay? And here, we need to have 28 on this side, okay? So because of that, we have 27 plus 1. So this one's going to be 28. Now, you have to, now with that, we see that it becomes 28 aluminum here. And so this is what it becomes. And then we go with this one. So we have 28, 13 aluminum. Then it undergoes a beta negative. And I'll write the reason why in just a second. And we see that. So it becomes plus 28. Okay. And then it's going to be 14 Si plus here. Okay. So right down here, I'll write what that means is we can do a beta negative mission because the nucleus has extra neutron. And that's through the neutron absorption, okay? That is because of, and let me do a little zoom here, that's because of this right here, okay? And it's talking about this. So then we can do the beta negative, and we get this answer right here. So we can write out 28. There we go. Silicon. And we'll write it out for you. Silicon. Okay, guys. Thank you so much. Let me put a little negative here so you can see it. Okay. Thank you, guys.
Welcome to Brain Vision.
Hi, everybody. So we want to determine the threshold energy of the deuterium H. I made my one a little too big. There we go. Plus another deuterium H. And here we have 3 helium plus a neutron. Okay. And here we can use this equation, and we have the masses of deuterium, and I'm going to denote that with a D. So this is called there we go. Okay. And we have that plus the mass of the other one. And you can always just multiply these by 2 if you want to get it quicker. But I'm just going to write it out for you. We have helium minus mass of the neutron times speed of light. Okay. And now we're just going to write out the masses. So yeah, I'm just going to do 2 times 2.01410 U. And that's just because there's 2 of these, okay? And it's just going to make writing this out a little bit easier. 16029 U is that mass, and then the other one is 1.08665 U. And we have the C squared here. And then we have 0.0003346 U. And we need to get this to MeV. So we're going to do our units here, 3.15 MeV, megavolts, and then we have divided by C squared. We have the U here, and we have the C squared here. So our units cancel out. And if you plug all this to your calculator, you'll get 3.112 volts. Okay, and this is your answer, guys. Thank you so much.
Welcome to Brain Vision.
Hi, everybody. So we want to know if this reaction is possible with a slow neutron. So we are given neutron plus 238, 92 uranium. Here we have 239 U, 92 plus gamma. Okay. And so a nuclear with a slow reaction, you can see that it's going to be, so I'll write that in red, nuclear reaction with slow neutron gonna look like 238 U 92, okay, plus 1 0 N, and it's still going to be the exact same thing here, 92 plus gamma, okay. So we need to find M initial, so I'm going to call it M initial here, the mass initial. And we can easily find that by just doing the neutron plus the mass of uranium here, which is going to be 238.0500783 U plus 1.08665 U. And this is going to equal 239.0594448 U. And this is atomic mass is given to us as 239.0542888 U. And we don't need to worry about this. So now we can use this equation. We have the Q value equals M initial, or and the initial minus the M final, and the speed of light. Okay, let me just scroll down. And let me just, that's gonna annoy me. There we go. Okay, so here we're just gonna plug in the information I just wrote down. 9448 U minus 239.0542888 U. Yeah, the speed of light. So with this, we have equaling to 0.00516 U, and we need to get into MeV. So we're just going to times it by 931.5 MeV divided by C squared. U here, C squared. Our units cancel out. Okay. Now we have 4.8064 megavolts. Okay. And since the Q value is positive, the nuclear reaction of a slow neutron is possible. Okay, thank you guys.